about the potential theory. So as I told you, it's very essential subject, so it's very important subject. And I promise you that I will talk about two-dimensional systems, because they are very important in science and in engineering also. So the starting point is that I want to explain that how to solve the Laplace equation in two dimensions. So this problem appears several places. For example, you have a corner like that, and electric spike, for example, comes from the sky, so it will be charged by the induced charge. So if you are standing here, and if this is the angle is alpha, so this is more safe for you, or you go to the lower one, for example, that. Which one will be the safe for you? So it means that which one will have more electric field. More electric field means more general, more dangerous. And the electric field here is a vector which the components are given as the gradient of the phi. And the phi, when there is no any charge, phi satisfies the Laplace equation. So two-dimensional problems are very important, like here, like many other cases. That was one of the interesting cases actually. So, or another example which will be very interesting is that you have a circle, and this circle is connected to the source of the potential, and you are standing here, so I want to know that what is the potential for you here, or how much charge will be induced here over the surface. This problem is also two-dimensional problem. Another problem which is two-dimensional is that you have a sphere. Sphere looks like three-dimensional, but you will see that. And this is the z direction, and we set a uniform electric field in the z direction. There is no any charge, nothing here. The thing is that you want to plot the electric fields. To know the electric field lines, you needed to know the potential. And you want to know that how much charge will be also induced over the sphere. So this is also related to the solution of this equation. And many more examples. So first I will talk about the solution of the Laplace equation in the Cartesian coordinates. So we have a region of the space like a circle, like this cone, like anything. And this is the any point inside that, so I want to find the potential here by solving this equation. So the technique which I use now is I want to pass to the complex plane and make this equation integrable. This equation, integration of this equation is not easy because this is a partial derivative, second order derivative with respect to the x. What I will do is not very conventional, but I will do like that. I will write this expression using the help of the this. Can we write that? Yes, if you multiply this bracket to this bracket, and if you think about the I like the complex unit numbers, so you can just see that this is equivalent to that. If I define a new coordinate, I call it z, and if I define another coordinate, I call it the complex conjugate of the z, immediately I will show you that this equation will be reduced to the simpler case. What does it mean? I try to convert all the derivatives to the z and z bar. Look at what happened. Partial x will be partial z, z with respect to x plus. This is just the chain rule. And from here, you can have x is 1 over 2 z plus z bar, and y is 1 over 2i z minus z bar. So partial z with respect to the x, what is will be? Partial z with respect to x will be 1. Partial z bar with respect to x will be 1. Partial z with respect to y will be I. Partial z bar with respect to y will be minus I. So look at that. What I can write here is that this will be partial plus partial. Nothing, just the change of the variable from xy to the z. You can do the same for the partial y will be I okay, and just replace it as here, partial x minus I partial y, and see what happens. Partial phi minus I partial y will be, look at what happened is that will be partial z plus minus I, and there is a one other I here, so minus I squared I minus 1 is, I square is minus 1, so this is a plus 1, so you see that these two will be cancelled. This 2, 5, you see it's very interesting. The two partial derivatives just reduce it to the one partial, why is it? And if you repeated that for this, for partial x plus I partial y, you see that that will be reduced to this. Anything can be seated here, huh? You can put at the phi or no. Even this equation, you can forget about the phi and write partial x is partial z plus partial z is over anything. So now I will use this expression and I rewrite the Laplace equation. When I rewrite the Laplace equation using this pair of the complex variables, so I will find that the Laplace equation reduced to the 4 this just. We can solve this equation very easily because you can just write this like this, yes? Just make a factor from one of the partial derivatives. What you understand from here, partial z bar is something is 0. It means that this is not function of the z bar. It's function of the z bar. So I call it this f of z. Okay? So what you understand from here, phi will be integral of f of z dz plus a constant which is not function of the z. Because if you take a derivative from the z, this term will be 0. Yeah? This is a z bar, it's not 0. And this you can write it like f of z plus g z. This is a phi of z and z bar. So I find the solution. So general solution for the Laplace equation will be phi x and y will be f z. What is the z? Z is x plus I, y, and x minus I. So any functions in this form is the solution for the Laplace equation. Any function. If you can write any function like that, it will be the solution for the Laplace equation. Or I generally I can write that any function of x plus I minus y will be the solution of this equation. Yes? For example, the charge, 1 point charge, seated in a point with the coordinate x and the y. For example, look at this function. Q over radical x squared plus y squared. This is the solution of Laplace. Do you know why? Because I can split this function to the x plus iy, x minus iy. So that is the function of the x plus minus iy. So this is a general solution for the Laplace equation. Yeah. But and the other things, for example, this function is also solution of the Laplace equations. Logarithm x squared plus y squared. This is also solutions. Again, if you split x squared plus y squared, it becomes like x plus iy multiplied to x minus iy. So this is also the solution of the Laplace equation in 2 dimensions. Yes? Still, you have any function of x plus minus y. You see that you find a test by looking on the function. You can see that this function can be solution of the Laplace equation or not. This is, for example, if somebody tell me that in the region of the space there is a function, I call it that arc tangent y over x plus y, and if he call it that for me the potential, I can say no, because it doesn't satisfy the Laplace equations. This is not in the form of x plus iy, x minus i. This is in the form of y over x plus y, something else. This is not, it cannot be the electric potential. Understand? It cannot be any type of the potential because it doesn't satisfy the Laplace equation. Because it's not in the form of x plus iy or x plus y. It's very good test. So it can be any function, but I cannot call it this potential. It's just function. You can take a derivative of that. There is no any physical meaning for this function. This function doesn't have any, but this has a meaning. This is actually the potential of the one long wire charge at the distance radical x squared. If you go to the holiday, you see that the potential, the electric field for the one long wire is 1 over r. And if you take the integral from that, you get logarithm r. So this is the logarithm. This is the potential. I just give the code to you that this is the physical example for these functions. What is the physical example for that? You know that. What is that? You have a charge, and the charge is located in the. This is the potential for the one charge. QR. All the example you can find it from fundamental physics. But this is nothing. This is nothing. We don't have any easy example of the physical problem which related to that. So this is the main difference between the work which I do as a mathematical physics and the work which the mathematicians do. So for the mathematicians, any function is functions. So If they give them this function, they calculate for the integral, derivative, but there is no physical mean for that. It doesn't have any. There is no any example in the nature which I can relate it to these functions. But there are these examples related to that. But this is the mathematical physics. So this is the general solution. So this is the general solutions. I mean, there is no boundary, there is no any charge, there is nothing here. You have it just to solve the Laplace equation here. You just solve the Laplace equation here and you find it out. So if there is a boundary, the situation will be changed. For example, if, as I told you, if I make a problem like that, if I have a corner or cone and the cone has the charge, you see that finding the solution for that is not very easy because you needed to check that. For example, here you give to the system a potential like call it V0. You needed to check that does this solution satisfy this condition here or not. So you will have the things which we call it boundary condition. If you have a boundary, you have to check the boundary conditions. Not any solution can be solution for this problem. I know that still Laplacian field is 0. Yeah, still. So one solution for this equation is that. Yes? One solution can be, as I write you, logarithm. Another solution for this equation even can be a radical one, or anything. But do all these functions satisfy the conditions? No. For example, this function never can give you V0 here. This function maybe can give you this V0 here. Huh? And this function maybe can give you V0 here, or maybe cannot. So, and this is I connected to the 0. So when you have the shape for your problem, so you needed to specify your boundary conditions. Not all the solution of the Laplace equation can be solved your problem like here. Or the other example is that, as I told you, we have a circle or I know the potential here is V0, and I want you give me the potential here at the distance R and the angle theta. Still, you know that the potential is satisfy the Laplace equation, and there are many solutions for Laplace equation. You see, I listed just 2 for you. You can find million solutions for the Laplace equation. Just any function in this form is the solution, yes? Just be clever at the right thing. So, but what is the solution which give me exactly V0 here? Huh? But this is a things which we never studied that before. We call it boundary conditions or boundary. So you have a boundary here, and you need to specify the solution which satisfies your boundary conditions. So now I want to talk about the solution of Laplace equations because as I mentioned last lecture, this lecture, next lecture, and maybe 2-3 lectures will be only about the solution of Laplace equation. We call it potential theorem. I want to solve either this problem or this problem, each one. So I think, I guess, maybe this is easier than that. You don't see that, but this is easier than that. Or anyway, either one of these questions I want to solve. And by solving this example, you will see that how to impose the boundary conditions. I will solve that because I like these questions. I will change the question that like this. So they will give you this problem. It comes in many subjects. It can come in the fluid dynamics. It can come in the electrostatics, in geophysics, and any subject. We have a cone like that.